Hi, in our previous video, we were discussing about a connection-oriented transmission protocol called TCP and about its features. In this video, we will be talking about one of the very important mechanisms handled by transport layer called congestion control. We will be discussing about principles of congestion control and how do we implement congestion control using TCP. But before we proceed, what exactly do we mean by congestion? Let us try to understand. We know that flow control is a mechanism in which you are trying to reduce the rate at which sender sends the data so that there is no overflow of data at the receiver. The overflow or loss of data at the receiver is concerned with flow control, but loss of data or overflow concerned with the channel through which the data is transmitted will be referred with congestion control. So if the traffic through the channel or the network is very high, then the capacity, it results in congestion. And how do we handle this congestion is dealt with congestion control mechanisms. Right. So congestion is all about too many sources trying to send too much of data to the network. So between source and destinations, we are going to have a channel through which you are trying to transmit the data. So here the network which is carrying the data from different sources to destinations is referred as network, and congestion may be occurring because of large amount of data flowing through this networks. So this is different from flow control mechanism. And what is the impact of congestion is, first of all, there will be loss of packets. For instance, this particular network which is connecting destinations with the sources is having limited capacity. So what happens? Till that capacity, the packets will be handled and slowly delivered to the destination. But beyond that capacity, the packets will be lost. In case if the number of packets is within the range of the network capacity also, but because of the more number of packets coming together, there will be a long delay in forwarding the packets to the destination. So congestion is considered to be one of the top 10 problems in a network. Right. Now let us try to look at what are the causes as well as the cost of congestion. In the scenario one, what we are trying to understand is we are trying to consider the capacity of the router or the network is infinite capacity. So here we have two senders and two receivers, but the router which is connecting these two senders and receivers is having infinite buffer capacity. So for instance, if the number of packets transmitted from both the users together is less than the capacity handled by the routers to forward, then all the packets will be forwarded without delay. But if the number of packets is more than the outgoing forwarding capacity of the router, they will be stored inside the buffer of the router. So in this scenario, there will be no retransmission or no loss of packet, but there will be a delay after certain duration. Here we can have maximum achievable throughput because there is no loss of packet, but there will be large delays when your network is congested. Now, having infinite buffer capacity is practically not possible. So let's take a real-time scenario where the routers which are connecting the senders and the receivers is having finite capacity. So our case 2 is a router with finite buffer capacity. So what happens is when the two senders are continuously sending till the capacity of the router, all the packets will be forwarded without delay. And later, once the beyond the capacity of the router, the packets will be lost. So here, when whenever a packet is being lost, the packet has to be retransmitted. So in our previous scenario, there is no retransmission, but in this scenario, we have to use for retransmission scenario because we are going to have lost packets. So in the traffic which has been traveling from sender to destination, not only we have the original data packets, but also we are going to have the retransmitted packets. So the finite shared output link buffers is reflected here, and these are the different senders, and here along with original data we will also have the retransmitted packets. Right. So let's have an effect of this particular scenario on throughput and delay of the packets. The perfect case is when the total data which has got the packets which are transmitting through the router is equal to the forwarding capacity of the router mentioned as lambda out. So in case if the total packets from source 1 and sender 2 is cumulatively less than or equal to lambda out, all the packets will be processed. So if this number of packets, that is lambda in, is greater than the lambda out, what happens is it will result in the loss of packets. And once there is a loss of packets, we are going to retransmit the actual plus retransmitted. Together we are representing with lambda in dash. So if lambda in dash is greater than lambda out, what is happening is retransmissions occur. And this will also make a delay in the packet transmissions. So here you could observe that initially when the total data forwarded by each of it sender is less than the outgoing capacity of the router, so your throughput is continuously increasing, and once it reaches to half of the capacity of router, because the router capacity is C, so each of this sender can send up to C by 2, and after that they cannot forward more packets. And also we can observe after C by 2 what happens is in the total packets which are transmitted, it is combination of actual plus retransmitted. So out of the C by 2 packets, only C by 3 packets are actual packets and balanced packets are retransmitted packets. So with more and more packets, what happens is the number of packets delivered from each source is getting delayed. So more work is required because of retransmission and unneeded transmissions when the link carries multiple copies of the packets. So these are the drawbacks in your scenario 2 where a router is having a finite capacity. Right. In our previous scenario, we are talking about 2 senders and 2 receivers. But here, let us take a scenario where number of senders is greater than 2. For instance, we are considering 4 senders and there are multiple hop paths. For instance, if A want to transmit to B, this is the path it uses. If A want to transmit to C, it will be using this particular path. And in case if A want to transmit to D, it has to use either this path or this path. So every path, a router is trying to carry multiple source and multiple destination data. And also when there is a packet loss, there will be a lot of retransmitted data. So as more and more retransmissions required, the actual packets get decreased and more will be the retransmitted. So lambda in dash, as we mentioned, it is trying to indicate the original data plus the retransmitted data. Right. When we are using multiple hop path, we need to understand to carry an actual data, a lot of upstream or additional data has been used. And whenever a packet has been lost, all this data we have the bandwidth which we have used for this upstream data. For instance, for 1 bit of data, I need 9 extra bits of information. So whenever a packet is lost, not only the data is lost, but also all this extra information has to be lost and to be retransmitted. So when a packet gets dropped, all the transmission capacity that has been used for that packet will be wasted. Right. The simple thing that we can understand from all the above discussion is congestion is not good for the network or sender or receiver. So how do we handle the congestion is what we discuss in the coming slide. Right. So far we are trying to understand what is a congestion and what are the causes of congestion. Now let us try to understand what are the different techniques we adapt to handle the congestion. So in general, the congestion is handled using 2 different approaches. The first type of approach is called end-to-end congestion control, and the second mechanism is referred as network assisted congestion control. Now in the first type, what we will try to observe is there is no specific or additional feedback given by the network to either of the sender or receiver. Then how do the sender or receiver will understand there is a congestion in the network is simple. When there is a delay in the reception of packets or getting the acknowledgement, or there is certain loss of packets in the transmission, then either of the sender or receiver need to understand there is a congestion. And this method, where no explicit feedback, but based on the system and its performance, we are analyzing the congestion, that will be referred as end-to-end congestion control. This approach is taken by TCP. Whereas in the second method of congestion control, here the network is either trying to provide a feedback to the sender or in some situations to a receiver about the congestion that has been occurred. And once a congestion has been identified, the sender is being expected to slow down the rate at which it has been trying to send the data. So what we try to do is the network will try to use a single bit to indicate to the sender that there is a congestion in the network, and it will be asking the sender to send the data at a bit lower rate. This is called network assisted congestion control. So earlier we were talking about what do you mean by congestion and what are the different types of congestion control mechanisms in the scenarios of congestions. Now we'll try to understand what is congestion control and how it is implemented in TCP, right? Right. The first method adapted by TCP is called as additive increase and multiplicative decrease mechanism. So what do we mean by additive increase and what do we understand by multiplicative decrease? Let us try to look from this graph. Now here you could observe that every time the transmissions are successful, so the number of packets delivered or the maximum segment size is incremented by 1. For instance, first time I sent 8 packets, next time I will be sending 9, next time 10, next time 11. So every successful attempt we are going to increase the congestion window size by 1 unit. So what is the congestion window? The amount of packets we are sending before waiting for acknowledgement. Just like sender window and receiver window in the flow control, for congestion control mechanisms, we are using another type of window called congestion window. So for additive increase, because every time there is a successful transmission without any loss, the number of packets will be increased by 1 unit. And whenever we find a loss or delay in the reception of packets, then we immediately go for multiplicative decrease. So what is multiplicative decrease is, before the congestion, in case if my total congestion window size is around 16 or 18 here, immediately when I identify a loss or delay in the packet, my congestion window size is reduced to half of my previous successful transmission. And again it is going to increase additively 9, 10, 11, and whenever again I find a congestion in the network, my congestion window size reduces to half of the previous success attempt. This method of increasing the congestion window size additively, and whenever a congestion is identified, decreasing the congestion window size to half of its previous size, that is called as TCP additive and multiplicative decrease. Congestion in a network is because of multiple users trying to transmit through the same network, resulting in congestion. There are two different ways in which we are handling it. The first one in which there is no assistance provided by the network, and we call it as end-to-end congestion control, where either the sender or receiver need to identify the congestion. Whereas in the other case called network assisted, you would find some assistance given by the network indicating either the sender or receiver about congestion. Now let us first have a look at the end-to-end congestion control, in which you will not find much assistance from the network. So in this, what is the thing that need to observe is, since no information is given about congestion, the sender need to take care about the total right. So here the sender will be trying to control the amount of data to be transmitted before waiting for acknowledgement. For this particular sender would like to calculate the congestion window size. So congestion window is the amount of data that a sender can send to avoid the congestion, for which it will be taking the reference of what is the last byte sent by the sender and what is the last byte acknowledged by the receiver. And the difference between these two must be less than or equal to the congestion window, so that there will be no congestion generated. The rate at which the data is transmitted will be calculated by congestion window divided by round trip time and is measured in bytes per second. Congestion window is a dynamic function. What does it mean? Means the congestion window size will be changing frequently as per the success ratio, and it's a dynamic function of the perceived network congestion. And how does the sender know about there is a congestion in the network? Because there is no assistance given. The different ways in which the sender can identify the congestion are: number one, there is a loss event where a packet has been sent and the sender did not receive the acknowledgement in the expected time, or there is a delay in the reception of congestion. So whenever the sender identifies the congestion in the network, it will be trying to reduce the congestion window size. In case if there is no congestion, it can increase the congestion window size, but whenever it senses a congestion in the network, it has to reduce the congestion window size. So there are three different mechanisms adopted by the sender whenever there is a congestion in the network. What are that? The first one is called additive increase, multiplicative decrease. The second one is referred as slow start, and third one is conservative after time events. Second method to control the congestion is called TCP slow start method. So what is the TCP slow start method is? Here in the first attempt we are going with a maximum of one maximum segment size. So for instance, your segment is of size 500 bytes. You'll be only transmitting one maximum segment, and after successful acknowledgement of that one maximum segment, we will be exponentially increasing until we find the first loss event. What it means is, first attempt we will send only one MSS, second attempt we will send two MSS, third attempt we will be increasing exponentially to square and so on. And this increase happens until we find a loss of packets. And remember, the available bandwidth here must be greater than maximum segment size by round trip time. And here the increase will be happen exponentially compared with additive increase in our previous method. Right. So as we mentioned, in slow start we start with one maximum segment, and when the connection begins, and this after every successful acknowledgement, the number of segments transmitted increases exponentially. So one, in second attempt we have two segments. After getting the acknowledgement, we'll send four segments and so on. So though the initial rate is slow, it ramps up exponentially fast in case of TCP slow start. Right. In slow start, till what point do we have this exponential increase? For instance, we have a congestion window size of around 16. So initially we'll start with one maximum segment. The next attempt it is 2. The next attempt it is 4. Next attempt it is 8. And at 8, the congestion windows, actually which we said is 16. So half of the congestion window size is achieved. So from here again we to go for linear increase. So till half of the congestion window we go ahead with exponential increase, and beyond that we go for additive increase. And this process will continue until we find a loss of packet. The small change that we have to observe in slow start compared with additive increase is, there whenever a packet is lost, the next attempt the congestion window is half of the previous congestion window, but in slow start, whenever a packet loss is been identified, the next attempt the congestion window is again reduced to 1, but not a half. And again here we will have an exponential increase till half of the congestion window and go for additive increase. So two major differences you could observe in these two methods are, there the addition is completely additive increase, and whenever a congestion is identified, you will be going for multiplicative decrease of half of the previous window. But in TCP slow start, initially we'll start with MSS equal to 1. We'll increase exponentially up to half of the congestion window, and from there we go for linear additive increase. Whenever a congestion is identified, this segment size is reduced to 1, and again we repeat the process. So here we are going to have variable thresholds, and we are going to adjust our congestion windows accordingly. Thank you. The third mechanism to handle the congestion is when we have duplicate acknowledgements and timeout event. What is the duplicate acknowledgement is? When we are sending number 1, 2, 3, but we are continuously receiving the acknowledgement only for 1, then it is a time indicate that there is a loss of segment for 1. So in that particular case, the congestion window is cut in half of the window size, which was previously, for instance, if it is 16, it cut to 8, and then it will be increasing linearly. So previous case, if we have sent 16 and we have got 3 duplicate acknowledgements, we'll reduce to 8 and slowly we go for linear increase. But so this through duplicate acknowledgements indicate that network is capable of delivering some segments. For that reason, we are only reducing to half of the previous congestion window. But whenever there is a timeout event, which means that we are not able to deliver the packets and we are not able to get the acknowledgement in time, in that case, the congestion window, instead of it is being set to a maximum segment size of 1. And again, the window will be increasing exponentially. Finally, after reaching to the half of the congestion, it will be increasing linearly. So here you adapt slow start, whereas in the first case we are adapting additive increase and multiplicative decrease. So these are the various ways in which we are trying to handle our congestion using TCP. So TCP Tahoe will be using additive increase, whereas TCP Reno will be implementing our TCP slow start mechanisms. Right. Let us summarize how the TCP is handling the congestion. The first method, so is slow start method. When congestion window is below the threshold, the sender is in the slow start phase. It starts with 1, but it increases exponentially. The second one is when congestion is above the threshold, the sender will be in congestion avoidance by moving from exponential increase to additive or linear increase. The third scenario is when we receive 3 duplicate acknowledgements, the immediate thing we try to do is we decrease our threshold to half of the congestion window and we'll set our congestion window to that particular threshold. And remember, in case of 3 duplicate acknowledgements, we start from half of the previous successful congestion window size. But whenever there is a timeout event occurred, the immediate thing that we try to do is we'll set our congestion window to 1 MSS and our threshold to half of the congestion window, and we are going for exponential increase. This is in summary about how congestion control is implemented using TCP protocol. Right, the table is trying to highlight the different scenarios which we have discussed and what are the actions that will be taken at the sender and what are the different comments on it. The first one is all about slow start method. We know that if acknowledgement for the previous has been received successfully, slow start will go for exponential increase. So every attempt which is successful, we are going for doubling of the congestion window. Whereas in congestion avoidance, what we are going to do is we are going for additive or linear increase, where the congestion window is increased by 1 maximum segment every time. So whenever you receive an acknowledgement for the previous one successfully, we are going to increase the congestion window size by 1 unit. Now in the slow start or congestion avoidance, if there is a loss event detected by triple duplicate acknowledgement. So if you are receiving a triple duplicate acknowledgement, then it means it's a fast recovery process. Before the timer expires itself, we will be retransmitting the last one. And one more important thing is we are going to decrease our threshold to half of the congestion window size and try to set our congestion window. Okay. The next event which you could find out is timeout. Whenever we have sent but we do not receive an acknowledgement, then what we are going to do is we are going to implement for slow start process. And when it is a single duplicate acknowledgement, we can either go for congestion window or threshold changed. Now let us try to determine what is the throughput of the TCP protocol as a function of window size and round trip time. For instance, we are talking about additive increase here. W is our window size before the loss is occurred or at the time of loss, and RTT is our round trip time. So W is the window size and RTT is our round trip time. The throughput is given by W by RTT. That is the ratio of window size to the round trip time. But immediately whenever there is a loss, the window size will be dropped from W to W by 2. In that case, the throughput is also reduced to W by 2 RTT. So if you take the average of this two, So average throughput will be 0.75 W by RTT. Right. So let's next talk about TCP fairness. In TCP fairness, for instance, there are K connections. In this reference, we have two connections. And if these K connections share the same bottle length of bandwidth R. So my total bandwidth is R and there are K sessions. So what should be happen? Each should be given an average rate of R by K. So for in this case, each of it will be given a share of R by 2. So is our TCP fair? Let's try to look at it here. So we know additive increase gives a slope of 1 for every time there is a linear increase in the number of segments transmitted. So as throughput increases, we have a slope of 1. Whereas in multiplicative decrease, what is happening is it's every time a congestion is identified, we are reducing to exponentially, and we would find a great reduction in the slope. So this is a simple diagram representing our how TCP is being sharing the resource and what is the slope for each of this case. Right. So TCP fairness we have been discussing in our earlier slide. But despite of this, why do people prefer UDP along with TCP? Very simple reason. The applications particularly related with multimedia often does not want to use TCP. The reason is simple. TCP is a connection-oriented protocol, and there have been a lot of mechanisms like flow control, congestion control. All this will be dealt by TCP, but our multimedia doesn't want delay in the transmission. So it does not want the rate to be affected by this congestion control mechanisms. So they opt for UDP. They feel that for pumping the data, audio or video at a constant rate, they can pump this audio or video at constant rate and they can tolerate certain packet loss. So what about this TCP fairness? As I mentioned earlier, that if the bandwidth rate is R and we have K parallel sessions, so here we can parallelly start number of connections between the two hosts. For instance, we are doing it in a web browser, and if there are 9 users who are sharing the bandwidth of R, and if the 10th user is being added, then it will be divided among the 10 users. So TCP is handling a good fairness among multiple connections. Right. So we have discussed about congestion control. How do we implement congestion control in TCP? What do you mean by TCP fairness? And what are the reasons for the preference of TCP over or UDP over TCP? So let me conclude our entire discussion on transport layer. That first we started with what are the principles behind the transport layer services? How do we implement multiplexing and demultiplexing in transport layer? What is meant by reliable data transfer and it is implemented in transport layer? How to implement flow control mechanism in transport layer? And what is congestion control, principles of congestion control, and methods of implementing congestion control in TCP? Then we talked about a comparison factor between the usage of UDP and TCP. Hope you have a good learning from this videos. Thank you.